Hey there, welcome to Galileo's AP STEM. Today we're covering topic 3.6 of the AP Calculus curriculum, so if your mind's ready to function, let's dive into calculating higher order derivatives. So what exactly are higher order derivatives? Well, we know that when we take the derivative of a function, say f of x, we get its first derivative, f prime of x. This tells us the instantaneous rate of change, or the slope of the tangent line. But what if we took the derivative of f prime of x? You guessed it, we get the third derivative and so on. These are what we call higher order derivatives. Let's quickly go over the notation for these. You'll often see notations like f prime of x, y prime, dy over dx, or d over dx of a function. But things get a little different for the second derivative. You'll see things like f double prime of x, y double prime, and even d squared y over dx squared, as well as the notation including the function. And if you have some insight, you'll know that this same pattern applies for the third derivative and so on. So let's jump into an example. Just look at this question. We have to find the first, second, and third derivatives of the function 5x to the fourth minus 3x to the third plus 2x minus 7. So this is pretty simple. 5x to the fourth will go to 20x to the third, 3x to the third will go to 9x squared, 2x will go to 2, and all whole numbers, as we know, negative 7, will go to 0. So from here on, it's just rinse and repeat. 20x to the third will turn into 60x squared, and 9x squared will go to negative 18x. Do it one more time, 120x minus 18. And do not forget the notation. For example, write f prime, f double prime, or f triple prime of x at the end of each of your equations. Or if you're feeling fancy, you can write dy over dx. Now that one was too easy. Let's try something a little more complicated. Let's say we have to find the second derivative of tangent of 2x times secant of 3x. Immediately, we know that we're going to have to use the product rule, because as we can see, tangent of 2x is being multiplied to secant of 3x. Remembering our product rule, we multiply the first variable, tangent of 2x, times the derivative of the second variable, secant of 3x. Since the derivative of secant of x is secant x times tangent of x, the derivative of secant 3x would be secant 3x times tangent of 3x. But wait, we're not done. We still have to multiply by the chain. This means taking the inside function, 3x, and multiplying by its derivative. Putting the first portion of the product rule together, we would get 3 times secant of 3x times tangent of 3x, also times tangent of 2x. Now onto the second part. This time we multiply the derivative of tangent of 2x times the normal version of secant of 3x. As we know, the derivative of tangent is secant squared, so tangent of 2x would go to secant squared of 2x. And obviously we have the chain, so we multiply by 2. Putting the second part of the product rule together, we should get 2 times secant squared of 2x times secant of 3x. Now if you look at both parts of the product rule, they both have secant of 3x, so we can just put it to the side and factor it out. Doing this, we get a final answer of secant of 3x, all multiplied by 2 secant squared of 2x plus 3 tangent of 2x times tangent of 3x. Now hold your horses because we are not done yet. We still have to find the second derivative. The first step to finding the second derivative is to notice the two parts of the function that we have so far. We have two functions being multiplied together. Remind you of anything? That's right, it's the product rule. On one hand, we have secant of 3x, and on the other, we have something much more complicated, 2 secant squared of 2x plus 3 tangent of 2x times tangent of 3x. Starting off, the derivative of secant of 3x as we did earlier is 3 secant of 3x times tangent of 3x. Now we just multiply it by the other function. And now we have the other part. We have to multiply secant of 3x by the derivative of the huge other function. Let's start by finding the derivative of 2 secant squared of 2x. And at first this might scare you because there's an exponent, what? But if you think a little bit, you'll remember that when we're dealing with exponents, we can use the chain rule. So you take the 2 down from the exponent and you multiply it by the 2 in the coefficient, which gives us 4 secant of 2x. The chain is whatever is under the exponent, so we also have to multiply by the derivative of secant of 2x. The derivative of secant of x, as we know, is secant of x times tangent of x, so the derivative of secant of 2x would be secant of 2x times tangent of 2x, also multiplied by the derivative of the inside function, which is 2. Multiplying it all together would give us a simplified answer of 8 secant squared of 2x times tangent of 2x. Now let's move on to the second part of the inside function, namely 3 tangent of 2x times tangent of 3x. And if your senses are pretty good, then you would be smelling the product rule. What we have to do first is multiply tangent of 2x times the derivative of tangent of 3x. And as we know, tangent of 3x would go to secant squared of 3x times the chain of 3. Then of course we move on to the second part of the product rule, where we multiply the derivative of tangent of 2x now times the normal version of tangent of 3x. And using the chain rule just as we did on tangent of 3x, tangent of 2x would go to secant squared of 2x times our chain 2. Putting this all together will give us 2 secant squared of 2x times tangent of 3x plus tangent of 2x times 3 secant squared of 3x, all multiplied by 3. And finally, we apply this huge expression back to the first part, do a little bit of distributing, and boom, we have the second derivative. And just like that, you've made it all the way through Unit 3 of AP Calculus. And in my dearest opinion, that deserves a medal. And although I can't give you that, what I can do is make you more AP Calculus videos. And if you do happen to need some more help in AP Calculus, because we all do, then go ahead and subscribe and check out the next video. I'll see you in the next one.